Last week, I discussed section 3 with you last week, which is basic special functions. Now today we go to start calculus of residues. Calculus of residues. So what we're going to do in this section is to introduce you how to compute residues and apply it to evaluate y is the imaginary part. What are the number in the imaginary part of y? So the real part of the complex number z is x, and the imaginary part is y. The set of complex number is denoted by c. I call it c. So that is the set of complex number. So we have some note. Every real number is a complex number. So the set of real number is a subset of the set of complex number. Meaning every real number is a complex number. A is a real number if a is equals to the real part. Now, if we are given x squared plus b squared equals to 0, and you want to solve x, you want to solve this, the solution to this problem is not a real number, it's a complex number. The solution is x equals to plus or minus bi, where your I is equals to the square root of minus 1. So as you did in your math 141, you can represent complex number in several forms. If you are given complex number x and z equals to x plus yi, you can represent it in what I call the polar form. In polar form, your z becomes r cos theta plus r sin theta I, where your theta is equals to tan arc y over x, and r is the square root of x squared plus y squared, what I call the modulus of z. So apart from you representing the complex number in a polar form, you can also represent it in exponential form. In exponential form, this same x, this same z, equals to x plus y, I can be written as z equals to r e to the power I theta. In this case, your r is equals to square root of x squared plus y squared, and your theta is tan arc of y over x. You can also represent your complex number in another form. So the real part is the first component, and the imaginary part is the second component. So this is basically a recap of what you know in your math 141, and which I believe will help you in the calculus of residue. So if you are given two complex numbers, this is the first complex number, and this is the second complex number. If you want to add them, or if you want to add or subtract them, so what you do is to add the real part together, and you also add the imaginary part together. So if you want to multiply z1, z2, this is the product where your I square is equals to minus 1. If I is equal to square root of minus 1, the I square becomes minus 1. So if you want to add z1 over z2, z1 over z2 is given as z1 over z2 times, you get the conjugate of z2 over conjugate of z2. So this will give you the product and the division of z1 by z2, where our z2 bar is called the conjugate of z2. So if z2 is equals to x2 plus iy2, then z2 bar is going to be equal to x2 minus y2i, which is called the conjugate of z2. In your 141, I gave you the De Morvis theorem. So if we write your complex number z in the polar form, you have a complex number z in the polar form. So you have your complex number z in the polar form. Then you can raise that z to the power of any positive integer. So to raise the power of positive integer is to raise the modulus, which is r to the power of n, and you multiply by, we multiply it to the power I theta by n. So z to the power n is just rn cos n theta plus I sin theta. So n is missing, n theta plus I sin theta. You can use the Morvis theorem to do the following. Number one, you can use the Morvis theorem to compute the powers of complex number, which is what we do here. You can use it to find the root of a complex number, and you can use it to prove trigonometric identity. So you can review your math 141. Some of these applications are there in your math 141. Okay, so you must know what an open set is and a domain in the complex plane. So what is an open set? So let me define what an open set is. So you have C to be the set of complex number. This is the set of complex number. You pick a point Z0 in the set of complex number, and you pick epsilon greater than 0. So we write B is Z0. This is just an open disk in C. So this is the set of all complex number in which the absolute value of Z minus Z0 is less than epsilon. So B epsilon Z now is what I call the open disk in set of complex number. In set of all the complex number Z in which the absolute value of Z minus Z naught is less than epsilon. So this is called the open disk in C, or we also call it the epsilon neighbor of Z naught. Now you have the set of complex number C, and you take a subset of D. This subset D is said to be an open set if every point X not to pick in D, you can always write a ball or a disk around that point. And that disk or ball is contained in that set. So your set D is open. If every point to pick in D, you can always write a ball on a disk, and that disk is contained inside D. Okay, for example, the open disk itself is an open set. So the open disk itself is an open set. Basically, we're talking about domain in the theory of residues. So what is a domain? So a subset which is non-empty of C is called a domain if it is open. So in this setting, every open set is called a domain. So every open set in this setting is called a domain, meaning that this is your set D, and this is your complex plane. This is your complex plane, and this is a set D. So this set D is open. If every point you pick in D, you can construct a ball around that particular point. So that is what an open set is. Let's give an example of open set. Number one, every open disk is an open set. This is an open disk. It's an open set. Every open disk is an open set. This is an open disk center at X naught with radius of R. The annulus is a domain. What is an annulus? Is set of Z in C such that you have R1 less than the absolute value of Z minus Z not less than R2. So every annulus is a domain. And so we have the third example, which is an half plane. The half plane and the closed disk are not domain. They are not domain. So these are examples that are not domain because they are not open set. They are not open set. Because of that, they are not domain. So the set that I have in 5.2, the set of all Z in C such that the image of Z, the imaginary part of Z, is not zero. It's not a domain. It's not a domain because it's not an open set. Okay, so we are going to introduce to what I call the complex function. So let's look at a complex function. So you pick throughout C, this is the set of all complex number. This is a domain in C. It's a subset of the complex field. We assume that the domain is not empty. So a function F that is mapping the domain to the set of complex field is a rule that assigns to every Z you pick in D, you have the image of Z. F of Z is called the image of that point Z. It's going to be in the set of complex number. So every point you pick in the domain, we always have an image in the set of complex number. So for the complex field, your complex function is taking F from the domain, which is a subset of C, into the set of complex number. So if your Z is written at X plus IY, because the domain is a subset of the complex field, so every point in the domain is a complex number. So it's written in the form of X equals to IY. So F is a function, is equivalent to you having two real function U of XY and V of XY, such that every function over this domain, a complex function, we always have the real part and the imaginary part. So F is a complex function, means we can always write two real value functions. The first one is U of X, Y. The second one is V of X, Y, such that F at any point in the domain can be written as the real part, which is U of X, Y, plus I, the imaginary part, which is V of X, Y. So this is the real part of the function, and this is the imaginary part of that function. So every complex function can be written in this form. F of Z is U of X, Y, plus I, V of X, Y, where S of X, Y, S and Y, they are real numbers. Okay, if we have a function, F of Z equals to Z squared, let's try to write F of X in terms of U of X, Y, plus I, V of X, Y. So if you have F of X is equals to Z squared, then what is U, what is V? So this is our F of X, F of Z, which is X plus IY, because our Z is replaced with X plus IY. So we have X plus IY to the power of 2. When you square this, we have x squared minus y squared plus 2ixy. So this is the real part. The real part is x squared minus y squared, which is our u of x. And the imaginary part, v of xy, is 2 of xy. So if you equate it with this, so that means the real part, which is u, is x squared minus y squared, and the v of xy is 2 of 2xy. Okay, so let's take another example. You have f of z to be equals to the conjugate of z. Z bar means the conjugate of z. So replace of z with x plus iy, and f of z is equal to the conjugate of z, which is x minus iy. So the real part then becomes x, and the imaginary part becomes minus y. So the real part is x, imaginary part is minus y. So we still try to write it in this form. So telling you that every complex function, we have the real part, which is u of x comma y, and the imaginary part, which is v of x comma y. So let's take this other example, which is the third one. We have f of z equals to 1 over z. F of z equals to 1 over z. Let's try to find the real part and the imaginary part. So your z is x plus iy, which is 1 over z, 1 over x plus iy. So to get 1 over x plus iy, you must get the conjugate of x plus iy, which is x minus iy. We divide by the conjugate, then you multiply. So this will give you x minus iy over x squared plus y squared. So that is x over the denominator minus iy over the denominator. So this is your real part. U of xy is x over x squared plus y squared, which is the real part of f. And v of xy will be minus y over x squared plus y squared. That is the imaginary part. Some of these are basic things you need to do. You need to know before you start talking about calculus of residue. We want to compute residue, that's our aim here. And we want to apply residue theory to evaluate integrals. So that is where we are going. But some of this basic knowledge is needed before we get there. So we want to talk about continuity of functions. Now you must know that here throughout we're talking about the complex functions. So you have a function f that maps the domain. This is a domain. A domain means an open set. By domain here, I mean open set. Open set means every point in it, you can construct a disk around it, and the disk will continue the set. So you have a function that maps an open set to the set of complex number. This function is said to be continuous at a point. The function f is said to be continuous at a point z not in the domain, if the limit as z tends to z naught of f of z equals to f of z naught. So f is continuous at this point if this happens. And f is continuous on the whole of the domain if f is continuous at all points in the domain. So the first one talks about continuity at a point z naught. And next talks about continuity on the whole of the domain. F is continuous on the domain if it is continuous at all points in the domain. Continuous at all points in the domain. So another useful thing you talk about is the notion of differentiability, differentiable, continuity, differentiability. So we also have a complex function. The complex function maps the domain, which is D, to a set of complex number. F is differentiable at this point z naught in the domain if the limit as z goes to z naught, f of z minus f of z naught over z minus z naught exists. If this limit exists, I denote the limit by f prime of z naught. If the limit exists, I denote the limit by f prime of z naught, and I said that f is differentiable at this point, which is z naught. So f is differentiable at the point z naught in the domain if this limit exists. And I denote this limit by f prime of z naught, meaning is the first derivative of f at z naught. So f prime of z naught is the first derivative of f at z naught. If the limit exists, we say that f is differentiable at z naught. Now, f is differentiable on the whole of the domain if it is differentiable at all points in the domain. With the differentiable at all points in the domain. Now, we need to note this very important condition that differentiability always implies continuity. If a function is differentiable, then it must be continuous. But a function may be continuous but not differentiable. So you must know that differentiability implies continuity, but continuity does not imply differentiability. So if a function is not continuous, it can be differentiable. Is that okay? But once a function is differentiable, it is automatically continuous. So you must know this very important fact. Okay. So we want to talk about holomorphic function. So if f is mapping the domain to the complex number is differentiable, then we say f is holomorphic. So holomorphic is the same thing as differentiability. So if your function that is defined on a domain, which is a subset of C, is differentiable on the domain, then the function is said to be holomorphic on that domain. So for now, just take differentiability as being the same thing as holomorphic. Differentiability, take it as holomorphic. So if f is differentiable on D and holomorphic on D, then we say f is holomorphic. So for now, not to confuse you, just take your differentiability as the same thing as being holomorphic on the domain. Okay, so if you want to show that a function is differentiable at a point, say a point z0 in the domain, so what to do is you must compute this limit. I'll give you an example now. You compute this limit. Once this limit exists at z0, then we say the function is differentiable at z0, and we denote the value as f prime of z0, which is the first derivative of f at z0. Okay, let me give you an example on how to compute the limit. So we have f of z equals to z to the power 2 on set of complex plane. So let us see whether f of z equals to z0 is differentiable on the whole of C, on the whole of Z, on the whole of set of complex number. So let's start with a point z0 in C. Let's start with a point z0 in C. By definition of the limit, so this is the limit at z to z0. Let's compute this limit. F of z minus f of z0 over z minus z0. Okay, the limit at z tends to z0. What is our f of z, which is z to the power 2? This is z to the power 2. So what is f of z0? F of z0 means that to replace your z0, replace your z with z0. We have z0 to the power of 2 all over z minus z0. Okay, the numerator is just difference of 2 square, which is z minus z0 into z. Z plus z not into z minus z naught. So z minus z naught will cancel out. So this guy will cancel out. Z minus z naught will cancel z minus z naught. So we have the limit as z to z naught of z plus z naught. So what do? Just replace your z with z naught. So you have z naught plus z naught. That is 2z naught. 2z naught. So the limit is 6. So this is a value 2 multiplied by that point. So your f prime of z naught is 2z naught. So the limit exists. Since the limit exists, it means that the function f of z equals to z squared is differentiable at z0. And since z0 is arbitrary, this is differentiable on the whole of the complex plane. For every z0 to pick in the complex plane, this limit exists. And the limit is 2 of z0. So that means the function f of z equals to z squared is differentiable at every point in C. Thus, the function is holomorphic on C. Differentiability, here as I've said, is holomorphic. So the function is differentiable on the whole of C, meaning that the function is holomorphic on the whole of the complex field. Okay, so I also want to talk about the Cauchy-Riemann equation, which is very important. Cauchy-Riemann equation. Now, I want to talk about the Cauchy-Riemann equation. So this is a theorem. So if you have your F mapping the domain to the set of complex field, you take your f of z to be equal to s plus iy. As I've told you, every function, every complex function, we have the real part, which is u, and the imaginary part, which is v. So suppose your f is differentiable at z0. Then, what is the condition? This is the partial derivative of u with respect to x. This is the partial derivative of u with respect to y. This is partial derivative of v with respect to x. This is partial derivative of v with respect to y. So if f is differentiable, then this partial derivative will exist at z naught. So your z naught is equals to s comma y naught. So that tells you that if your f is differentiable at z naught, then the first partial derivative will exist at the point z naught. That is first condition. The second one is that u of x at z naught must be equal to v of y at z naught. U of y at z naught will be equal to minus v of y at z naught. Is that okay? So this equation 4.2 is very, this second equation is very important. It's what I call the Cauchy-Riemann equation. So the equation 4.1, which is Sodoma figure 2, is what I call the Cauchy-Riemann equation. So if I give you a complex function, I can ask you to check whether the function satisfies the Cauchy-Riemann equation or not. So you have a function which is f of z. F of z is differentiable if the first condition holds, which means it has all its first partial derivative, and 2, it satisfies the Cauchy-Riemann equation. So as I've said, 4.1 is what I call the Cauchy-Riemann equation. So the Cauchy-Riemann equation is necessary for differentiability, but not sufficient. The Cauchy-Riemann equation, once you have this one, is a necessary condition, but it's not sufficient. But the sufficient condition will be that all the partial derivatives are continuous. So the sufficient condition will be that all these partial derivatives in one must be continuous. That is the sufficient condition. So Cauchy-Riemann equation is just a necessary condition, but it's not a sufficient condition. Okay, so let's give examples to show that the function satisfies the Cauchy-Riemann equation. So the question says, check whether the following function satisfy the Cauchy-Riemann equation. So I take my f of z to be equal to the modulus of z. F of z equals to the modulus of z. Modulus of z is x minus iy. So that means my u is x, my v is minus y. So what is my u of x? U of x means differentiate u with respect to x, which is 1. U of y means, v of y means differentiate v with respect to y, which is minus 1. So you discover that u of x is not equal to v of y. So that means the Cauchy-Riemann equation is not satisfied. Look at the Cauchy-Riemann equation, which is at 4.1. So this is Cauchy-Riemann equation. U of x equals to v of y, u of y equals to minus v of x. So if this equation is satisfied, then we see that the function satisfies the Cauchy-Riemann equation. So the first example does not satisfy because u of x is not equal to v of y. So it does not satisfy the Cauchy-Riemann equation. Okay, let's take another example. Let's define our f of z as the modulus of z. F of z is defined as the modulus of z. Modulus of z, by definition, is just x squared plus y squared. This is modulus of z. So let me just say plus 0i. This is invariably 0. It has no much. It has nothing to the equation. So in this case, my u is u squared, x squared plus y squared to the power half. My v is 0. Okay. So differentiate u partially with respect to x. We'll get this guy. Since my v is equal to 0, differentiating with respect to y will be equal to 0. So that means u of x is not equal to u of y. So the function does not satisfy the Cauchy-Riemann equation. So this function, f of z equals to modulus of z, does not satisfy the Cauchy-Riemann equation. Okay, let's take another example. So here I take my f of z to be equal to e to the power of z. F of z to be e to the power of z. So replace of z with x plus iy. So z is x plus iy. So f of z equals to e to the power of z becomes e to the power of x plus iy. So which is to the power of x dot e to the power of y. E to the power of iy is just equal to cos y plus I sin y. So this guy here is just the same thing as cos x plus I sin y. So when you multiply this out, that means your u of x will be e to the power of x cos y, and v of xy will be e to the power x sin y. So differentiate this partially with respect to x. You have e to the power of x cos y. Use your product rule. Differentiate v partially with respect to y, meaning that this e to the power of x becomes a constant. You have to the power of x cos y. So differentiate u with respect to y. You get minus es sin y. differentiate v with respect to x, we have ES sine y. So we have your UX is equals to VX, and you have your VS equals to minus UY. So the function satisfies the Cauchy-Riemann equation. So example 3 satisfies the Cauchy-Riemann equation. Satisfy the Cauchy-Riemann equation. And since all the partial derivatives are continuous, it means that the function is differentiable everywhere. Okay, so let me give you another example. So our f of z is sine z. Sine z. So you know that your z is x plus iy. Use the formula of sine a plus b. So sine x plus iy will give you cos x, sine s cos iy plus cos s sine iy. Cos iy is sitting as cos y. And sine iy is sitting as sine iy is sitting as sine y. So that means your u is sine s cos y, and your v is cos s sine y. So now, if you differentiate with respect to x, you discover that your u of x, differentiate this partially with respect to x, it will be equal to differentiate partially with respect to y of v, and u of y will be equal to minus v of x. So you see that the function f of z equals to sine y satisfy the Cauchy-Riemann equation. Okay. You can also check the next example, f of z is equals to log z. So log z also satisfy the Cauchy-Riemann equation with what I have there. Okay, so don't let me waste much time on this. Now, we want to go to an analytic function. These are functions that we are going to make use of in our calculus of residue. So analytic function. So what is an analytic function? You must recall throughout that your f is a complex function. Your f is a complex function. So your complex function f of z is said to be analytic on z naught. If you can write it in this form. Is that okay at z naught? So your f of z, which is a complex function, is said to be analytic on z naught if it can be represented at the neighborhood of z naught by a power series of this form. So whenever you can write your f of z at z naught as the power series in 4.2. So f of z will be said to be analytic at that point z naught. In some sense, in some cases, it will not be difficult for you will not be able to write it in this form. In that case, we say the function is not analytic. But once you can write your f of z at z naught in this power series form, so we say that your function f is analytic on z naught. So function f is analytic on z naught. So if you can write your f of z is this power series form, which is summation k equals to 0 to infinity a k z minus z naught raised to power k. Now there are several things you can bring out from the power series. The power series converges for some point that is not equal to z naught if it is absolutely convergent for all points that is nearer to z naught. Now if it is continuous at this point z naught, you can always find what I call the circle of convergence. You can always find what I call the circle of convergence. Inside that circle, the series converges absolutely for all z inside the circle of convergence. The series diverges outside the circle of convergence. And on the boundary of the circle, two things can happen. The series can either converge or diverge on the boundary of the circle. All this we did in your Maths 141. You can just have a recap on what I taught you. I think I taught your class Maths 141. All this I taught you in Maths 141. So this is your power series. So let's go up a bit. You have a complex function f of z. F of z is analytic at this point z naught if you can write it in this power series form. So if you have f of z is this power series form, you can differentiate it. So let's go here. You can differentiate f of z in that power series form. So when you differentiate f of z, this is what you're going to get. This is what I call the circle of convergence of the power series. The circle of convergence of the power series is here. R is the radius of convergence. This is the circle of convergence. So you can differentiate the second time. If you differentiate the function the second time, invariably as differentiating in the power series, you're going to get this. Differentiating the third time, you're going to get 4.5. So you can continue in that way. You can get the nth derivative of that power series, representation of that function. You can also integrate. You can also integrate along a given path. We can also integrate along the given path. So if you want to integrate along the path P, so it's just you taking the summation now, you integrate point by point. So you can also integrate to have your 4.6. Okay, let's try to have the power series of some basic functions. Let's have the power series of some basic functions. So if you have f of z is equal to 1 over z minus 1. So look at your f of z. If your f of z is given as 1 over 1 minus z, the power series will be equal to summation k equals to 0 to infinity z to the power k. So if your f of z, please don't forget this. This you can do yourself. You can always find the power series of any finding function, which you already know in your mass 141. So if your f of z is equal to 1 over 1 minus z, this is the power series of that function. Since f of z can be written as this power series at z not equals to 0, so it means that f of z is analytic at 0. F of z equals to 1 over 1 minus z is analytic at z naught. In this case, my z naught is 0. Okay, so if you take your f of z as e to the power of z, take your f of z as e to the power of z, you can always write it in terms of this power series. So e to the power of z, this is the power series of e to the power of z. So that means your function f of z equals to e to the power of z is analytic at z naught equals to 0. And z naught equals to 0. So this is it. So take f of z to be equal to sine z. This is the power series of sine z. This is power series of sine z. So that means f of z equals to sine z is analytic at z naught equals to 0, because we can write it in this power series form at z naught equals to 0. F of z equals to cos z is also analytic at z naught equals to 0, because we can write it in this power series form. So this is the power series of f of z equals to cos z. This is for sine. This is for e to the power of z. Okay, this is very important. Every analytic function is homomorphic. So some books, some textbooks will not differentiate between analytic or homomorphic and differentiability. Some books will use the theory and meaning the same thing. Analytic, homomorphic, differentiability. Some texts will say they are the same. Okay, so let's go to Taylor's and Maclaurin series. You already know Taylor series in 141. The new thing you are learning here is the Lorentz series. Lorentz series is very important. Please pay attention to Lorentz series. Lorentz series will lead us to the notions of singularity, notions of singular point, regular point, and how to compute residue. So next week I will start computing residue. And once you know how to compute residue, you can use your residue theory to evaluate integral. That is where you are going. Where we are going is that I want to teach you in this section how to compute residues of functions. And by the time you compute residue at a point, and how to use that to evaluate integral. So let's go to Taylor's and Lorentz theorem. We know Taylor's theorem from our Mass 141. The new thing we are learning here is just the Lorentz theorem. So Taylor's theorem is very straightforward. Lorentz theorem is just you allowing the expansion to have the negative power of z minus z naught. Okay, what is Taylor's series or Taylor's theorem? So if you have your function f of z that is holomorphic at all points inside the region gamma. So f of z is holomorphic means it is differentiable at all points in the region. Holomorphic means it is differentiable at all points to pick in the region. So at the region, maybe you take the region to have a center at z naught. So you can write your f of z in this series form. This is what I call the power series of f of z. So 4.7 is called the power series of f of z at the point z naught. Power series of f of z at the point z naught. So how do you compute your a of k? This is formula for computing a of k. So a of k is just this one means you differentiate f k times all over z naught over k factorial. So if you want to compute a of 0 is just f of z naught. A of 1 means differentiate f once, put z naught and over k factorial. So 4.7 is what I call the power series of f of z at z0. When your z0 equals to 0, we have Maclaurin series. So whenever your z0 is equals to 0, we have Maclaurin. So all these are Maclaurin series. Look at the example that I gave up. So this is a Taylor series at f of z. This is a Taylor series of f of z equals to 1 to 1 minus z at z0. So this is a Maclaurin series, a case in which z0 is 0. So if f of z equals to e to the power z, so this is the Maclaurin series, Taylor series at z0 equals to 0. Taylor series at z0 equals to 0 of sine z. And this is a Taylor series at s equals to 0 of cos s. This is this guy. So now the power series or the Taylor series of f of z at z0 is given as 4.7. So how do you compute your AK? So this is the formula for computing your AK. AK is the kth derivative of f at z0 over k factorial. So that is your the power series of f of z. So look at it. A function is analytic if and only if it is holomorphic. I've said it before. A function is analytic if and only if it is holomorphic. So thus, it means analytic and holomorphic and differentiability, they are almost the same. They are the same. You can take them as being the same. Okay. So now you can use the you can find the Taylor series of some elementary function using these three important series. So if I give you any function and ask you to find the Taylor series of that function, you can come here and use for 4.7. So if you want to find the Taylor series of any function, so this is the Taylor series of any function. If you want to compute, this is what to do. So what you need to do is just to find your AK. So this is formula for finding your AK, and plug it here and you go. But apart from using 4.7, you can also, apart from using 4.7 to find the power or Taylor series of any given function, you can at the same time use any of these elementary functions. Is that okay? So if you are giving f of z to be e to the power of z, this is the Maclaurin, this is Taylor series at z0. So if you are giving f of z equals to e to the power of z, the Taylor series or the power series at z0 equals to 0 of f of z is this series. Okay, that's the exponential series. Don't forget this. But in case you forget this, just come here. In case you forget this, just come here. Make use of 4.7. Make use of 4.7, 4.8, and z0 equals to 0. Then you are fine. But if you can put this in your mind, that is fine. You don't need to go to 4.7, 4.8 to compute it. So this is the Taylor series or the power series of f of z equals to e to the power z and z0 equals to 0. So if f of z is 1 over 1 minus z, if f of z equals to 1 over 1 minus z, then the power series at z0 equals to 0, Maclaurin series is this guy. Summation k equals to 0 to infinity, z to the power k. So if you replace your z here with minus z, so if you replace your z in the first part with minus z, then the power series at z0 becomes minus 1 to the power k all over z to the power k. This is the circle of convergence. Circle of convergence is modulus of z less than 1 because here your z0 is 0. Z0 is 0. So the circle of convergence for this and for this is just absolute value of z less than 1. Okay, the next one that we can use is what I call the binomial series. So if f of z is 1 plus z to the power of n, so the binomial series or the Maclaurin series or the power series at z0 of f of z is summation z equal to 0 to infinity and combination k, z to the power of k. So this guy here is the power series at z0 equals to 0 or the Maclaurin series of f of z equals to 1 plus z to the power of n. And the circle of convergence is modulus of z less than 1. So radius of convergence is 1. Circle of convergence is modulus of z is less or equals to 1. Okay. So now, if you use your 4.9 and this definition, so you can always write your coshjet at e to the power z plus e to the power of minus z over 2. You can always write your shine z as e to the power of z minus e to the power of minus z over 2. So if you write that, So you can, if you make use of this and this, you can always write your cosh z. You can always write your cosh of z as summation k equals 0 to infinity z raised to the power 2k all over 2k factorial. You can also write your shine z as summation k equals 0 to infinity z is over 2k plus 1 all over 2k plus 1 factorial. Now, your e raised to the power iz. E raised to the power iz, by definition, the power series of it at z not equal to 0 is summation k equals to 1 to infinity I raised to the power kz k over k factorial, where I is just root of minus 1. So this is the z to the power k of that. Cos z is the real part of this, so which is the same thing as this, similar to what we obtained earlier. The sin z equals to the imaginary part of e to the power of iz. So this is what we will get. Okay, let's give an example now. So we want to find the Taylor series of this function at z not equals to 1. If you want to find your Taylor series, look at what I'm going to do. You can use your 4.7, 4.8. If you want to find the power series or the Taylor series, just make use of this is of your Taylor series or the power series of f of z as z naught. And this is how to compute your AK. So you can make use of this to compute the power series or Taylor series. That's one way. Another way of computing power series, sometimes it's a bit technical. So you can always make use of this. Let me tell you, you can always make use of 4.7, 4.8. You can always make use of your 4.7 and 4.8. Where is 4.7? To compute, to find the power series of any given function. So where is 4.7? So to find the power series of any function, complex function at z naught, always make use of 4.7 and 4.8. 4.7 is the power series, so you don't need to compute your AK using 4.8. But if you are smart enough, you can use some of the established series that I've discussed earlier to compute it without using 4.7 and 4.8. So for example, I want to find the Taylor series of f of z equals to shine of 2z minus 3 about z not equals to 1. I want to find the Taylor series of f of z equals to shine 2z minus 3 about z not equals to 1. I don't want to use 4.7, 4.8. I want to use any of my established series. Okay, look at what I will do now. Shine 2z minus 3. I can write 2z minus 3 as 2 into z minus 1 minus 1. You have to do some manipulations here. Then look for the formula of shine A minus B. So shine A minus B will be equals to shine A cosh B minus cosh A shine B. So take your A to be equals to 2 into z minus 1. Take your B to be 1. So shine A minus B is equals to shine A cosh B minus cosh B shine A. So if you do that, now we have a value for shine 2 into z minus 1. So we just put your z as 2 into z minus 1 in 4.12. And you put your cosh, you put your z as 2 into z minus 1 into 4.2. You go to 4.12 and 4.13. If you go to 4.12, you have a formula for computing cosh. Look at cosh. This is cosh. This is cosh z. And this is shine z. So if you want to compute cosh, you want to compute cosh 2 into z minus 1. You only replace your z with 2 into z minus 1 here. To compute shine z, to compute shine 2 into z minus 1, you replace your z with 2 into z minus 1. So if you replace it in 2.13 and 2.12, so then you're going to have this. So replace your z as 2 into z minus 1 in 4.12, and replace your z as 2 into z minus 1 in 4.13. So that means your shine of 2 into z minus 1 becomes this guy here. This is your cosh 1. And your cosh into 2 to z minus 1 becomes this guy here. So this is the power series or the Taylor series of this function at z not equals to 1. So you see that instead of using your 4.7 and 4.8, then I use any of my elementary series to compute the power series. Okay, so let's look at this other example. Find the Taylor series of f of z. This is f of z about z not equals to 0. Okay, So what I will do first is to resolve f of z into partial fraction. This is my f of z. When you factorize z squared minus 5x plus 6, you go to get z minus 2z minus 3. So z over z minus z minus 3, in your 141, I taught you how to resolve it to partial fraction. So when you resolve this to partial fraction, you are going to get this. Now you discover that z is equals to 3 and z equals to 2 are the singular points. Note, I will start talking about singular points next week. Singular points are points in which the function is not regular. So the singular function of a function f of z is the point at which the function is not regular, meaning the function is not differentiable at that point, meaning that the function is not continuous at that point, or the function is not defined at that point. It's called that if you put z equals to 3 here, you get 0. The function is not defined at 3 and at 2. So z is equals to 2 and 3 are called the singular points of f of z. Okay, so take the first one, which is 3 over z minus 3. So which you can write as this. So what we do here, divide each term by minus 3. If you divide each term by minus 3, you're going to get this. So now put your z. Put your z as 2 as put your z as z over 3. Put your z, look at this expansion that I have here. Look at this expansion for 1 over 1 minus z. 1 over, okay, look at this expansion, 1 over 1 minus z. Look out. 1 over 1 minus z gives you summation k equals to 0, z is to power k. So in that expansion, you just put your z as z over 3, then you are done. So you place your z here with z over 3. So let's go down a bit. If we go down a bit, so now we have this. So your minus 1 is out. You replace your z as z over 3. So that will be summation k equals to 0 to infinity, z over 3 raised to power k. This is this. So this is the radius of convergence of this power series. That is z over 3 less than 1. So the radius of convergence is 1. So this is the circle of convergence of that series. Okay, for the second one, which is this guy here, divide each term by minus 2. So you get this. So go to what you have, do the same thing here by replacing your z as z over 2. So you have this. Then substitute both into f of z. F of z is 2 over z minus 2z minus 3, which is this. So replace 3 over z minus 3 as this guy here. And replace 2 over z minus 2 as this other guy here. So this is what you're going to get. 1 over 2k, 1 over 2 to power 2 raised to power k minus 1 over 6 to power k. You factor it as z to power k. So this is the power series. This is the Taylor power series of the function f of z equals to z over z squared minus 5z plus 6. So what I'm saying is that you can either use 4.7, 4.3 to find the power series, or you can use any of the established elementary series to do the computation. Okay, so you can do the same thing for this. We can find the Taylor series at this at z not equals to 0. So this is also a very straightforward thing to do. Not to waste my time, I want to go to Lorentz series because I don't want the. So let me go to Lorentz series and round up with it. So the difference between Lorentz and Taylor series is that Taylor series only take the series in terms of the positive powers of x. Or the Lorentz series, so a Taylor series is a series of positive powers of z minus z naught, because z minus z naught are raised to the power of positive numbers. So if we allow z minus z naught to be raised to the power of negative integers, then we're talking about Lorentz series. So Lorentz series allow z minus z naught to be raised to the power of negative number. So Lorentz series is just you generalizing the idea that you have in Taylor series by allowing your z minus z naught to be raised to the power of negative number. So that is Lorentz series. So let's look at what the series is. So if you have your f of z to be analytic means that you can write f of z a power series at a point. So now we allow f of z to be analytic on two circles, concentric circles, circle 1, circle 2. Meaning that at every point in this circle C1, you can write f of z as a power series. At every point in this circle C2, you can write f of z as a power series. So the center is at z0. Now, f of z being written as summation k equals to 0 to infinity, akz minus z0 to the power k, plus summation k equals 1 to infinity, bk z minus z to the power of minus k. This is what we call the Lorentz series of f of z, Lorentz series. You see, the first part have the positive powers of z minus z0. So these are positive powers of k. Why these are negative power? From k equals 1 to infinity of bk, these are positive powers of z minus z0. So you have the positive powers of z minus z0 plus the negative powers of z minus z0. That is the Lorentz series. But for Taylor series, you will not have the negative powers of z minus z0. For Taylor series or the power series, you only have this side. You only have this side. This side will not be there. So if this side becomes 0, if the second series becomes 0, your Lorentz series becomes your power series. So if it's not equal to 0, in such a way you have the negative powers of k, negative powers of z minus z0, and positive powers, you have the Lorentz series. So this is how to compute your AK, and this is how to compute your BK. Don't bother yourself about this for now. So the basic things you want to know is that the Lorentz series is just a generalization of the power series or the Taylor series, such a way that you allow your z minus z0 to have both the negative powers and the positive powers. That is the Lorentz series. So, but look at this very important remark. If the function is analytic on and inside the circle, whenever your function is analytic, meaning that the function is differentiable inside and on the boundary of the circle, then the whole of this becomes 0. In that case, your Lorentz series becomes your Taylor series. Is that okay? So that is what we have. BK will be 0. And if BK is equals to 0, so you put BK equals to 0 here, so that means all of this will be 0 for OK. So that means your Lorentz series becomes the Taylor series. So whenever your function f of z is analytic on the boundary of the circle and inside the circle, it means that your Lorentz series becomes your Taylor series. Okay, so another remark is that the rest expansion of a given function in a given region is unique. You only get a unique expansion. You can't get two at the same time. So no expansion can be used to find Lorentz series. So the expansions that you already know, you can use them to find the Lorentz series of any given function. Finding the Lorentz series of any given function means that you want the powers of z minus z0 to be negative and also to be positive. So that is what you want to do. Okay. So now let me give one or two examples, then I stop. So let's expand f of z to be equals to e to the power of 2z all over z minus 1 squared about the singular point. What is the singular point? As I've said, from next week, I will start talking about the regular point and the singular point, and I will use that to compute the residue. Singular points are points in which the function is not regular. Is that okay? The singular point of a function is the point in which the function is not regular, meaning the function is not differentiable at that point. But when you look at this function, f of z equals to e to the power 2z over z minus 1 squared, the function is not regular at z equals to 1. So that means the function is singular at z equals to 1, because at z equals to 1, this is not defined. We put z equals to 1, the denominator becomes 0. The function is not defined. So the point at which the function is not defined is the point at which the function is not continuous, and at that point, the function is not regular. So those points are called the singular point of the function. So we want to find the Lorentz expansion of this function at the singular point. So this is having only one singular point, which is 1. And we want to determine the region of convergence. Okay, what I'm going to do here is that I will make use of my known expansion to compute the Lorentz expansion and the Lorentz series of this function. So I want to find e to the power 2z into z minus 1 squared So which I can write as this. So if you look at the numerator, we have e to the power 2z, e to the power minus 2. When you multiply to the power 2 and to the power minus 2, you get 0. So you see how this is power 2z. So this numerator is not the same thing as this one. Okay. So this is power 2z over z minus 1. This is power 2z over z minus 1. So I only have this guy. So this is power 2 all over z minus 1 square. So I want to find the expansion of this guy. The expansion of this guy is just you putting your z as 2 into z minus 1 in the expansion of e to the power of z. Then you get this. This is what we will get. This is what we will get. This is what we are going to get. E to the power 2 is a constant, take it out. Then when you multiply this, you have this power k minus 2. Now this is not the Lorentz expansion. Because look at it. If your k is equal to 0, you get minus 2, which is a negative powers of s of z minus 1. Your z naught is 1. If your k is equal to 0 and 1, if your k is equal to 0 and 1, you will be getting the negative power of z minus 1. So this is basically, if you stop here, it's fine. If you stop here, it's fine. This is the Lorentz expansion of f of z. But if you go further, it's okay, so that you can make us to see what you are doing. So this is a case in which your z is equal to 0, you have this. A case in which z is equal to 1, you have this. You put your z, if you put k equals to 2 plus m, then you have this. So this is the negative powers of z. This and this are negative powers of z, while this is the positive powers. So this is the power series part, and this is the negative powers of that particular z. So this is the Maclaurin, this is the Lorentz series expansion of f of z. Okay, you can do the same thing for this guy here. You can find you want to find the Lorentz series expansion of f of z with different regions of validity. So f of z is equal to z over z minus 1 to the power 2. So what are the singular points of this function? The singular point at z equals to 0 and z equals to 1. Because at z equals to 0, the function is not defined. At z equals to 1, the function is not defined. So z is equal to 0 and 1 are the singular function of that function. So you can write a 1 over z. 1 over z, this is the power series of 1 over z. So it follows that what you have there is w 1 over z, which is this, e to 1 over z minus 1 square. So you multiply the whole of this by z minus 1 to the power of minus 2. This is what we will get. So this is one way. And this is the modulus of convergence. This is radius of convergence of that Maclaurin's and Lorentz series. For the second one, you can write 1 over z in terms of this series. Then 1 over z is 1 over z minus 2. So this is 1 over z. Then multiply by z minus 2. So you discover that this one is having, when k is equal to 0, you are going to get a negative power of z minus 1. When k is equal to 1, k is equal to 2, you'll be getting the negative powers of z minus 1. So let me see. We have another example here. So we want to find the Lorentz series expansion at z equals to 2 for this function. So this function is f of z equals to z over z squared minus 5z plus 6. Resolve to partial fraction, you get this fraction to that fraction. So that means those two singular points of this function as z equals to 3 and z equals to 2. We always find residue about the singular point. So at z equals to 3 and z equals to 2. So what we want to do is that for this first expansion, as I did the last time, so you can write this one in terms of this series. So if you write that in terms of this series, you only multiply by the second one, which is 2 over z minus 2 over z minus 2. So you just replace 3 over z minus 2 with this series, which is this, and you multiply by this. So then you are done. So the region of convergence of this series is the whole of the plane. It's all of the complex number except 2. So that is, you just punch the circle at this point, z equals to 2, z not equals to 2. So this is the circle, the region of convergence of that particular Lorentz series. Okay, so basically what we have done is just to review some basic things about the complex function theory, and I've talked about the issue of power series and Lorentz series. Next week, our interest in this chapter is to teach you how to compute residue and to use the residue theory to evaluate integrals. We are going to first of all teach you how to compute residue. We spend time on that. By the time you know how to compute residue, you can then use the residue theory to evaluate some complex integral. And we can then apply this to heat equation and wave equation. That is basically what we are going to do in the next 2, 3, 4 weeks. So and I'm going to stop here for today. The thought for this week is not much. It's just for you to find the power series and Lorentz series. I put it on Moodle for you. Tomorrow, I want you to spend tomorrow on to prepare for your exam, for your test. Your test is Wednesday, 7:45. The test is starting. I'm going to put it online. The test will end by 8:45. And I've told you, the test will not cover what I've taught you this week. The test will only cover what I taught you last week. So take time to revise what I've taught you last week. I will not examine you more than basic special function. So the whole of the test will be on basic special function. So spend tomorrow to go through what I taught you last week. I will not put the Zoom on for tutorial tomorrow. I want you to spend tomorrow to revise your notes. There will not be tutorial tomorrow. Okay, I don't know if you have one or two questions for me to